Hello everyone, welcome to today's lesson on oscillations and simple harmonic motion. Okay, our conversation starts with a review, and we're going to review springs. All right, I have a little tiny spring here. All right, we can pull it, we stretch it, we know it exerts force on this thing. And to review, our spring force equation is F equals kx. All right, remember this is how strong this spring is, and x is its displacement. Now the spring force is known as a restoring force. What that means is regardless of where the object is, the spring is always trying to restore it to its equilibrium spot. All right, we saw this in a diagram here with our classic spring on a frictionless surface. If I attach a spring to a block and I stretch that spring out, that spring is going to exert a force to try to bring it back to its equilibrium spot. All right, notice the displacement is that way, but the force is the opposite way, and that's why there is technically a negative in front of that to show that the x and the f are different directions. All right, but if we go to this one, if I compress the spring, all right, notice that the spring still tries to push it back to its spot. So the spring force changes direction depending on displacement. It always wants to push this thing back to this spot. Now that's a review, all right, to get us back into the discussion of springs. Where this lesson is going to go is what would happen over time. If I stretch this thing out and let it go, well, what's going to happen? Well, we know it's going to come back to here, but at this point, it's going to be moving and it's going to go to the other side. Well, once it goes to the other side, the spring is going to push it back to the middle. Once it gets back to the middle, well, it's going to keep on going, go out here, and then the spring is going to pull it back to the middle. It's at this point here, it's going to go to the other side, and it's going to keep going back and forth, back and forth. And that repeated motion is known as, well, we'll call it several different things. All right, these are all technically a little bit different, but for us in this general basic lesson, it's all going to be the same thing. We refer to that as oscillation. Something is oscillating back and forth. All right, and a specific type of oscillation is called simple harmonic motion. Now there's stipulations to what makes something simple harmonic motion and just oscillations, but we're not going to get into that. We don't need to. All right, basically, a simple harmonic motion oscillation is anything that's going back and forth, a to and fro motion. It's going to keep repeating itself over time. All right, and that's what we're going to kind of look at in today's lesson. And while this is a fairly short lesson, it is a good start and a good basis for things we're going to look at in the future, because they're kind of based off things that are oscillating. All right, so we have to cover these basics before we can hit more interesting topics. All right. Okay, so let's look at our little setup here. We have our classic mass on the end of a spring, all right, and right now it's in equilibrium. Now, if I give this thing a displacement, all right, and I let it go, it starts oscillating back and forth around its equilibrium point. Now it starts to sway back and forth, all right, but if I let it go good enough, all right, it'll just oscillate back and forth, and that's the type of motion we're talking about here, all right. Now for a little bit of vocabulary on oscillations, so we know what we're talking about as we move on. All right, these definitions here are not unique to oscillation. We saw these in circular motion. All right, period is the time for one complete cycle. So on our demo here, if I let this thing go, it'd be the time for this thing to go all the way up and then all the way back to the spot where I let it go from. All right, and you can see on this thing, all right, it's a pretty quick period. The next one is frequency. All right, frequency, the definition of that is always the number of something per time. All right, the number of something per time, and in this case, it'd be the number of cycles per time. All right, how many times does this thing go up and down in a second or half a second or whatever time? And how long does that thing go up and down in an hour? Whatever something per time is always a frequency. All right, we know from before that these are inverses of each other. All right, if I do one lap every 2 minutes. We're talking about circular motion, all right? So my one lap every 2 minutes, that would be one lap per minute. That's my frequency. So what is my period? What is the time to go around once? Well, 2 minutes. 1/2 is the frequency, so 2 is the period, all right? Now, for the sake of oscillations here, you can kind of visualize and think of the frequency as the rhythm. How many times does it get back there? It's going to more or less keep that rhythm, all right? So think of the frequency of this object as a rhythm, because we're going to talk about that in a little bit, all right? By the way, notice how rhythm is spelled. I had no idea how to spell it. I didn't know that the only vowel in there was a Y. So there, you learned something else different by this lesson. All right. Now the last definition we have is amplitude. All right, and that's just the maximum distance it travels from its equilibrium point. All right. So we look back at this diagram here. If I let it go, if I stretch this thing all the way out to here and then let it go, this X would just be called A. All right, that's all that means. So its amplitude is how far it oscillates from its equilibrium point. All right. So if I had this thing here, there's its equilibrium point. That's where it's stationary. If I bring this thing down 5 centimeters and let it go from 5 centimeters, then it will travel to the equilibrium point, travel up 5 centimeters, and go back equilibrium point, go down 5 centimeters. So its maximum displacement would be 5 centimeters. That's what we call the amplitude. All right, the largest that thing can get from just being even. All right. Okay, so the next thing to look at briefly is a graph of simple harmonic motion, because it's pretty classic. All right. What this is a graph of its displacement versus time, and what we can get from this is where it's located at any point in time. All right. So for this, for our original demo, here's our equilibrium point, and that is represented by the horizontal black line. All right. Now, when I bring this thing down, that has a negative displacement, because we're going to say that down is a negative direction. All right. So when I let this go is when time starts. All right. When I let this go is when time starts, and you can see on here, where does it start? In the negative displacement. All right. And then as I let this thing go, it's going to travel through the middle up to the top, highest amplitude, back down, sorry, to the equilibrium, and then back down to the bottom amplitude. And it's going to continue to do that over time. And that is what our graph is showing. Starts at the bottom, it's going to go to the highest amplitude, and as it goes on, it just keeps going back and forth. But you can imagine, as this thing goes up and down, if I were to put a marker on here and let this thing go, and that marker could draw a path on the whiteboard, it would draw that blue line. All right, as I move this thing, in other words, as time goes on, it would draw that blue board. You can see go up and down, up and down, up and down, up and down. All right, and it would give us this graph, which you should recognize as a sine or cosine curve. In this case, it is a, what is it? Since it starts down at amplitude, it is a cosine curve, but the shape, sine and cosine, are actually the same. All right. We're going to see more math and equations that go with oscillation in a different lesson, because this is concept-wise, there's not that much, but mathematics there can be a little bit more. All right. Okay, so we're going to look at the relationships here between amplitudes, the masses, the springs, and its frequency, which means we're also looking at it with respect to its period, but it's a little bit easier to recognize the frequency of this thing. All right, so let's take a look at this demo, and we'll change a couple of things to see how one affects the other. All right, so with this particular mass and this particular spring, I'm going to set it into some harmonic motion oscillations by giving an initial displacement. All right, and let's see what the frequency is like. All right, just a little displacement, and there's the frequency. There is the rhythm. Every time it gets back down where it starts, that is the frequency. All right, now what we want to figure out is, all right, what we want to figure out is if I give this thing a bigger displacement, what happens to its frequency? In other words, what happens to its rhythm? All right. you would think if I, well, let's see. If I just give it a little bit of displacement, all right, just a little bit, there is the frequency. There is the beat. Get that in your brain and remember what happens. Now I am going to give it a bigger displacement. Let's see what happens to the period. Is anything happening that is different? Is this beat different? You should be able to hear that the frequency and the rhythm is exactly the same. And it does not matter how far the thing has to move. All right, so that is practically the worst rap ever. All right, I do not see myself having a new career in there in that respect. But what it does illustrate is that the amplitude of this thing does not affect the frequency, and therefore it does not affect the period. All right. You would think if we talk about the period part of it, if I bring this thing down more, then it would take more time for it to cover more distance. So you would think bigger amplitude, bigger period. All right. More distance it has to cover, so it's going to take more time. Well, remember our initial equation for spring force, F equals kx. If the displacement is bigger, the force is bigger. So what happens is, even though if I only press this thing down a little bit, there's only a little bit of force pulling it back over this little distance. But if I pull it a big distance down, then there's a bigger force, which means it's going to pull it quicker to cover that larger distance. And it turns out the relationships almost like balance each other out. If I pull it further, it gets more force, so therefore it can cover more distance in the same amount of time. Whereas here, if it's just a little bit, it's a little bit of force, so it doesn't pull it as much, so it doesn't have to go as fast to cover that smaller distance, keeping the period and therefore keeping the frequency the same, because period and frequency are just inverses. If one directly relates to the other. If one stays the same, the other has to stay the same. So that's why when, regardless of what the amplitude is, the period would stay the same. And that is a classic multiple choice question on the AP exam, on pretty much any exam with oscillations. They would ask, what happens to the period if you double the amplitude? And the answer is nothing. Everybody wants to say it doubles, it gets cut in half. The answer is nothing. Amplitude has no effect on period. Amplitude has no effect on frequency. All right, it's a setup for like a trick question. Now we could see, well, what does affect period? Okay, so let's test out to see if we can find something that affects period. All right, and frequency. I know they're inverses, but one directly depends on the other. So let's get back into our head the rhythm / the frequency / the period of this thing. I'll just give it a little bit of displacement. And that is the frequency of that. So if we change the displacement, nothing new will happen. So the only thing I can change is the mass. So let me change the mass and I will make it a smaller mass. Let's see what happens to the frequency. And it's going a lot faster, and now my rapping skills and the song is totally killed. All right, so I changed the mass and the frequency changed. All right, clearly this is a lot faster rhythm. All right, a lot faster rhythm. So mass affects period, and let's figure out this last thing. All right, I got a smaller mass. And it's a lot faster rhythm. all right? So smaller mass, frequency goes up, all right? If I increase, so likewise, if I increase the mass, it's a lot slower frequency. So increase the mass, frequency goes down, all right? So they're inverse relationships as well, all right? Okay, so that is our introduction to simple harmonic motion and oscillations, all right? It's a pretty simple, basic lesson, half review, but it's a good building blocks for the other phenomena we're going to look at in nature, in physics, which is a little bit more exciting, all right? But without these vocabulary words, period, frequency, amplitude, and knowing where they're coming from, the other stuff is not going to make much sense, all right? So thank you for watching. I hope that rap song that I made right up on the spot with that particular frequency, I hope that doesn't stick in your head too long. I know it was a really good song, and that's pretty talented considering I did it, right off the top of my head. If you want to try that, you have the frequency and you can come up with your own thing. Be my guest. But anyway, thanks for watching, and see you when I see you.